Ever wonder how your phone knows to suggest that weird but oddly perfect snack recipe at 2 a.m.? Or why your streaming app suddenly starts pushing shows you've never heard of? It's all powered by recommendation systems, those invisible helpers that analyze your behavior and guess what you might like. But here's the secret. These systems aren't just helping you find content. They're also being tested by sneaky attackers who want to mess with the results. Today, we're diving into a mind-bending research breakthrough that's changing how we think about these systems. Scientists are uncovering how fake user profiles can be engineered to look scarily real, using a technique called conditional latent diffusion. Let's break down the science behind this digital illusion. Imagine you're a master artist, but instead of paint, you're using math. The goal? To create fake user profiles so convincing, they could fool even the most advanced algorithms. That's what conditional latent diffusion does. It starts with a latent space, a hidden layer where user and item data are stored as mathematical patterns. Think of it like a secret codebook that holds the essence of how users interact with products or content. Here's the magic. The system doesn't just copy existing patterns. It refines them. Using a process called denoising, it gradually adds details to these patterns, turning blurry sketches into lifelike profiles. It's like training a robot to mimic a specific person's habits without them ever knowing. This is where dual cross-attention comes in. It's like having two guides, one focusing on the user's preferences, the other on the items they interact with. Together, they steer the fake profiles to behave exactly like real ones. But wait, how do they avoid creating copycat profiles that all look the same? That's where dispersive regularization saves the day. This technique ensures the fake users are diverse enough to avoid suspicion. It's like teaching a group of clones to have unique personalities so they don't stick out. By mathematically pushing these profiles apart, the system prevents mode collapse, a fancy term for when everything starts looking identical. What does this mean for the real world? These methods aren't just theoretical. They're revealing how recommendation systems can be both vulnerable and resilient. On one hand, attackers could use these techniques to skew results, like promoting fake products or manipulating reviews. On the other hand, understanding these strategies helps researchers build stronger defenses. So next time you get a recommendation that feels too perfect, remember, behind the scenes, it's a battle between clever algorithms and the ever-evolving tactics of those who want to game the system. Thanks for watching. Hit subscribe if you want more deep dives into the tech shaping your world. And let me know in the comments, what's the weirdest recommendation you've ever gotten? Ever wonder how AI creates fake profiles that almost feel real? It's not just magic, it's math, creativity, and a little digital alchemy. Let's break down the secret sauce behind these lifelike simulations. At the core of this tech are latent representations. Think of them as the DNA of generated data. These are the hidden patterns a neural network uses to encode information, like a blueprint for what a fake user looks like. But here's the catch. If the network gets stuck in a loop, it falls into mode collapse, where every output starts to look the same. It's like painting a mural with just one color, boring and unoriginal. To fix this, researchers invented the dispersive loss, a clever trick that pushes the network to spread out its creations. Imagine you're painting again, but this time you deliberately mix different colors. The dispersive loss does something similar, nudging the network to create diverse latent representations. A parameter called temperature tau acts like a knob. Lower values force the network to really push apart similar data points, creating a wider spread in the latent space. The result? A more vibrant, varied set of outputs. Why does this matter? Well, a wider spread means higher entropy, a measure of randomness. Higher entropy means the AI isn't just copying patterns, it's exploring new possibilities. This also ties into covariance, which describes how different traits, like age, location, or interests, relate to each other. By expanding the volume of these relationships, the model avoids overfitting and creates more realistic, varied profiles. But how do we know these fake users are actually stealthy? Researchers use a suite of metrics. Take the Mahalanobis distance. It's like a statistical deviation meter, showing how far fake users stray from real ones. A low score means they blend in. Then there's KDE likelihood, which estimates how likely a fake user is to fit into the real data's density, like checking if a puzzle piece matches the bigger picture. Here's a twist. Some metrics measure uncertainty. The RVC-Entropy, for example, gauges how confused a classifier gets when trying to tell real versus fake users apart. The higher the entropy, the better the disguise. Meanwhile, GSA degree checks how well fake users integrate into the network structure, like seeing if a new person fits into a social group. All these pieces, conditional alignment, cross-attention guidance, and dispersiveness, work like a team of artists. One ensures profiles match specific targets, another injects guidance at every step, and the third keeps things fresh and unpredictable. The result? Fake users that aren't just realistic but targeted, perfect for testing systems without risking real data. It's a dance between control and creativity, proving that even in AI, diversity is key. Next time you see a generated profile, remember, it's the product of math, creativity, and a little bit of digital alchemy. Thanks for watching. Stay curious.